In the world we live in, this sort of mesoscopic world, here's a good SAT word for you. So in the mesoscopic world, this middle thing, the math and physics really agree really, really closely, extremely closely. But when we're talking about like galactic style stuff, right? How do you measure how far away a star is? You're not
Right.
measuring the centimeter. You're measuring this to the nearest like astronomical unit, but you also have to consider like how gravity is bending light, right? I mean, this is a very different realm of physics. The mathematics is the same, but the physics has actually changed. The same exact phenomenon happens at the quantum level, right? Quantum mechanics has its own set of rules, these physical rules that are not in this world that we live in, right? They're mostly counterintuitive. So we have things like the uncertainty principle, right? In the big world we live in, we don't have to worry about this. And there's, I'll give you a joke, right? A friend of mine once said, I got pulled over for speeding, and the cop said, "Do you know how fast you were going?" And my friend said, "No, but I know exactly where I was." I mean, he was a physicist, and like that was a really nerdy joke, but people who have studied quantum mechanics are like, actually, that's a good point. But in this world, we can know how fast we're going and where we are kind of simultaneously.
Right.
There's some error there, but we're not concerned at 10 to the minus 35 electron volt seconds. That's not an hour consciousness, right? So I mean, this ends up being the point. At quantum computing, there's this energy scale that we have to consider. There's actually a large energy scale and there's a small energy scale.